Hey class, Adam Ward here. I want to talk with you about spill models, and this lecture video is going to go along with lecture 10 out of your textbook. And so firstly, let's take a look at what we've done thus far this semester. One of the first things that we did was work on CSTRs. And so if you could picture the world as having a space defined by time, space, and concentration, we've basically explored what I did in red on the screen here. We fixed space, considered one CSTR or a few CSTRs, and we looked at the time series response. That was our general solution and our particular solution. Over the course of the last few lectures, we started to work on distributed systems. So we let things vary through space, but we fixed time by making these steady state solutions. And what we're going to do today, and what Chopra addresses in lecture 10 of his textbook, are what we call spill models. And so these are going to be models where velocity lets things move in space and in time, and we try and calculate these solutions of concentration as a function of both where we are and when we're interested. So that's going to be our objective in this lecture. Now, the mathematical basis for this is something that's called the continuous time random walk model. Chopra calls it a drunkard's walk model. The idea here is that if you start in the middle and you were having an equal chance of either stumbling to your left or stumbling to your right, odds are that you would do that in about equal proportion. So if you start with mass m in the middle, 50-50 will move either way. An alternative way to think about this, if you watch a group of folks coming out of Kilroy's on Kirkwood at 2 in the morning, you might see about half of them stumble toward traffic and half stumble away. Now, as you go another time step, half the people who stumbled to their left, drawn in purple, might go left again, the other half might go back to the middle, and half of the folks who stumbled to the right might then take their second step, stumbling either left or right. And so you start to get this distribution that spreads out in the edges, but still remains higher in the middle. You can imagine that continuing to happen through time and ultimately generating something that's shaped like a bell curve. Now, the mathematical description of this is about the probability of movement. So what are the odds that I move to a particular place given some understanding of how big my step is going to be in space, delta x, and how much time between when you observe my two locations, delta t. So this is the mathematical equation that describes that probability. I don't have any expectation that you memorize it. If we want to understand what concentration does, we can take the mass that we started with, that initial m at the very top of my drawing on the right-hand side, and multiply it by that concentration. So how do we get concentration as a function of x and time in this case? We simply replace probability with concentration, replace that 1 with the total mass that began there. So I want to talk first about an instantaneous pulse, because I think this is the easiest one to get your head around. And this is applicable for a conservative solute, so we'll add reaction later in the lecture. Now, if that's the case, our mass balance equation looks something like this. dc dt is equal to, and we've got just the diffusive term on the right-hand side. And if we do some calculus magic, we can get an explicit solution here as a function of x and t. Now, what does that mean? Right? That actually means you could plug in any value of x at any time and calculate the concentration at that place. The mass in this is the total mass divided by the cross-sectional area of what you're trying to study. And so with no flow, if we look at what things might look like at time equals 0, where we have some spill that's fixed in one location, at some future time, t1, things have started to spread out symmetrically, and as time progresses to t2 and t3, that spreading continues. So you get perfectly symmetrical spreading, but the center doesn't move because, of course, there is no advection. Now, the next wrinkle we'll add is a similar scenario, but with flow. Now, what happens if you let things start to move? You still get symmetrical spreading, but that spreading is happening through time as this moves sort of down the river or down the conveyor belt, if you want to think of it that way. So we get the exact same shape. All we're doing is shifting it in time because velocity is scooching the whole response curve in the downstream direction. Now, I want to pause here and talk just briefly about what spills look like. So on the bottom left, I'm drawing out exactly what I drew on the last page, this symmetrical spreading. Right, so if we took snapshots at 3 different times, represented by these 3 different colors, we would see perfectly symmetrical spreading. That's called a Lagrangian approach to the world. Lagrange, a mathematician who did his work as though you were moving with the flow, moving along with the pulse of concentration. So if you imagine you were in a boat at the same time a spill happened, as you moved, if you looked left and right, you would see symmetrical spreading. But that's not how we typically make our observations. It's much more common that we observe in an Eulerian framework. And the idea here is that you have a fixed monitoring location. So maybe that's a bridge that's easy to monitor from, maybe that's a USGS gauge where you have discharge, but you're standing at a fixed point in the world watching the stream flow by. And so if that's the case, the rising limb might look the same to you. You'd see this sort of gradual, gentle transition of diffusion having spread things out. But the back end is not going to be symmetrical with the front end. The back end of that is always going to have a slightly longer, what I'm calling a tailing behavior, or this late time concentration. Right? Why is that? Why do we see late time if we fix our observation location? Well, if you think about the mass coming by you later in time, it's had longer to diffuse. Right? So the red part of that signal has already come past me, it can't affect me anymore. But the purple side, even as the beginning has passed by me, the upstream portion is still diffusing in the upstream direction. So you'll get just a little bit of asymmetry from that, and any other storage processes that might delay that mass movement can create extremely long tails or contaminant legacies in the environment. Okay, so we looked at a solution if there was no advection. Now let's add advection to the mix. So our mass balance looks something like I've drawn in purple. And we can end up with a solution that looks like this. The concentration in x and time looks like the mass per cross-sectional area divided by 2 times the root of pi et. And then we've got that whole quantity times e to the minus x minus ut squared over 4et. So what changed? The only thing that's changed by adding advection is up here in the exponent, what I've circled in red. Now you've got that x-coordinate being adjusted by velocity and time. Right? So essentially, same solution. All we're doing is adding a little modification to the coordinate that makes it shift through time. And finally, you might say, well, okay, but what if it reacts? So here's our advection, dispersion, decay, or advection, dispersion, first order reaction equation. We've added that minus Kc term out on the right. And again, the solution is incredibly similar. In fact, all we've done is add this minus Kt term in the exponent. So these start to look very, very similar, and mathematically that's because they're underpinned by that same continuous time random walk. We're just adding some adjustments for advection and adding some adjustments for decay. And just a note here, you could also address settling with this equation. You could either explicitly include it up in the mass balance, or you could convert that settling rate into a first order reaction rate equivalent and plug it into the equation that's shown here. I want to take a look at a few more items that might be of interest. When we did particular solutions for a single CSTR, we looked at things like step loads and ramp loads. I want to show you just a couple of those and some of the heartache that comes with them in these spill models. So first, let's look at a continuous release of infinite duration. So basically a step load. Now, I'm not going to write out the solution here because it's a fairly cumbersome to write, and I don't think that looking at it adds much to our understanding. Some of the notation that Chopra uses, and this is equation 10.25 in your textbook, the estuary number, which again is that first order reaction rate times the diffusion coefficient over velocity squared. And he defines sort of a lowercase r that is 1 plus 4 times the estuary number. The other thing that you might not have seen before in that solution is noted as ERFC, and those are all written in lowercase, I believe, in your textbook. That's known as the error function complement. and the error function complement is 1 minus the error function. Which, of course, begs the question, what the heck is an error function? An error function is a mathematical function, and for our purposes, we're going to leave that sort of as a black box. Historically, you would have either calculated this or had a textbook or a reference book that would have had values of the error function that you would look up. For our purposes, we're going to take the error function and essentially acknowledge that we're never really going to be solving this problem by hand. Error function, you can find websites to calculate for you, or this is a built-in function in programs like Excel, R, MATLAB, and so forth. So when you look at that equation, I just want you to be able to address where these terms come from should you find the need to use it in your homework or in your future careers. So that's an infinite duration. What if we had a step load of a finite duration? So for example, a tank began to leak, it got empty, and then the load cuts off. We get a solution that looks something like this. For times that are less than tau, so times before this turns off, you go ahead and use equation 10.25 out of your textbook. So just like you would have done for a step load. For times after what Chopra uses a tau to define here, use equation 10.29, which is an even uglier adaptation of 10.25. And so with these equations, and with the level of detail we're covering them, do I have any expectation that you will be solving these by hand? Absolutely not. Do I think that you should be able to plug these into Excel and solve them if you needed to? Yes. Will I ask you to solve this on a quiz? That would seem awfully unfair. It seems reasonable that I'd ask you to set up a problem like this, but certainly not to solve it with the complexity of those equations. You'll notice in your textbook the subsequent lectures start to look at more advanced numerical methods. And I think that you probably get a sense with as complicated as these equations get to be, solving these analytical problems tends to be pretty cumbersome. It gets to be a little bit easier to do the numerical approximations. So we discussed forward Euler in class, for example. Gets to be easier to do that than to actually continue deriving these highly idealized analytical solutions. Okay, so we've seen the world get more and more complicated as we account for more and more processes and as we up our demands of what we want in space, what we want in time. I wanted to end by revisiting the estuary number. And of course, this is giving us some understanding of how dominant advection is in comparison to reaction and spreading. And so Chopra suggests that a system is diffusion dominated if your estuary number is much larger than 1. Both terms matter if you're about equal to 1, and you're advection dominated if you're significantly smaller than 1. Now, what does that mean in practice? If your estuary number is greater than 10, that would probably be a reasonable range where you could ignore velocity. Right, now you've got a system that's more or less dominated by diffusion and symmetrical spreading. So you might be able to pull a simpler equation to make reasonable estimates. If you've got a really small value, you're going to ignore dispersion. And so that takes us back to thinking of the world as a plug-flow reactor. Plug-flow reactor equations were pretty easy to work with, and so we can feel good about that. Finally, if you're in that sweet spot of about 0.1 to 10 for your estuary number, I'm thinking full advection dispersion equation is required, and I'm thinking that the spill model equations we're deriving today are probably the ones that I would be looking at. All right, so we've talked through spill models. We've basically written out our mass balance and shown some of the analytical solutions for different cases of loading. At this point, I expect that you could select which of those analytical solutions is correct, and that you could plug some values of x and t in and actually produce a time series at any 2 points. And I expect you to be able to describe something about the difference between Eulerian and Lagrangian approaches to the world. So do we move with the pulse, or do we stand on the bank and watch the pulse go by? It's an important framework to have in your head, particularly if you're ever monitoring a spill and you see the rising limb, you see the peak, and your colleague says to you, oh great, we just mirror that over the axis and we know what the tail will look like, I want you to remember that it's not quite that simple and there's more work to be done. All right, thanks everybody, and I'll see you in class. Have a great weekend.